Hi everyone, welcome to day 16. Day 16 is the last big cock concept we're going to see. It's a really important one, and it's one of the maybe really distinguishing concepts of the kind of formalism that computer scientists tend to do. It's inductively defined propositions. That's why this chapter is named IndProp, inductive propositions. Inductive propositions are how you define the set of things that you believe are true. And in Coq, we'll get to do that similarly to how we used the inductive keyword to define the data that we work with, only this will be defining new propositions, new things that you prove. So an inductive proposition will define the forms of evidence for the various propositions that we care about. These are a key tool for reasoning about invariance and sort of like letting us just do interesting proofs. These kinds of inductive invariants are sort of the classic computer science technique for, say, proving programs correct, proving theories correct. They show up absolutely everywhere. Let's take a look. So we're going to start with a concept we've seen now two different ways. We're going to see it in a third way. Let's talk about evenness. Okay, so we've seen two notions of evenness. We wrote a function even b that just decided for a natural number. It computed, hey, is this true or is this even or not, right? And it would return true when it was. And then we said, once we learned about the existential quantification, like the exists proposition, we said, okay, well, another way to say that a number n is even to say that is to say there exists some k such that n is twice k. Now, there's another way we can talk about evenness. We could say, look, even numbers are formed according to the following rules. Here's the different ways you can show evidence for evenness. I'm going to give two rules. The first rule, which I'm going to call ev0 or ev0, is that the number 0 is even. This is like a ground rule. The term of art is this is an axiom. Right? We're just going to say, hey, we believe this is just the case. We're going to say 0 is even. The next rule that I'm going to call EVSS says that, look, if the number n is even, then the number s of n is even. Right? These are two rules. You can think of it as saying, look, an even number is either 0 or you add 2 and then that's to an even number and you get another even number. This is a recipe for finding even numbers. It's how you count up by even numbers. Hopefully it makes sense as a definition. We'll see as we continue that it's equivalent to these other two definitions that we've seen before. A classic sort of computer science, like programming languages, logic form of presentation, is to use inference rules. So that is a rule that looks like this. I'm going to briefly talk about the anatomy of them here, but I'm going to make a whole video dedicated to just thinking about and working with inference rules and derivations and so on. We'll see what all that is in the continuation. So an inference rule for an axiom, like EV0, just has a line and then a conclusion below the line. So the general anatomy here is premise 1, blah, 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 premise n. You have the premises above. And then down below, we have a conclusion. And you can read it as saying, well, look, premise 1 implies premise n implies conclusion. Right? This is, on some level, all you really need to know about inference rules. But for us, we can go into a little bit more detail. So here we're just saying, look, there's no premises. We can just assume it is the case that EV0, the proposition EV0, holds. Why? Well, here's the proof of it. We named it. We're going to call it rule EV0. We made up the rules, so we get to decide what counts as evidence. Okay, here's another one. So here we have one premise. EVN implies EVS of S of n. So we would write that in this implication notation this way, as saying, well, look, there's a theorem, EVSS, that says, hey, if n is even, then EVS of S of n is even. So the way to read these rules is say, if you can find the things above the line, the premises, then you can safely conclude the things below the line according to the name of the rule that we just saw. Okay, so once you have these rules, you can draw proof trees. Again, you'll see these written on the whiteboard, and I think it'll be a clearer thing, but we can look at it for now. Where, how might we prove that 4 is even? Well, EV0 proves that 0 is even, just by fiat. That's rule 0, EV0. And then EVSS lets us see that 2 is even, because 2 is the successor of 0. And then another EVSS lets us see that 4 is even, because 4 is the successor of 2. Right? This is what's called a derivation or a proof tree, showing that 4 is even according to our rules. Now, hopefully you agree that 4 really is even, which means maybe our rules are doing a pretty good job. Okay, so putting that all together, we can write in Coq, hey, here is how evenness looks. So EV is going to be the name of the property we're caring about, the property of naturals, that says you give me a natural, I'll tell you whether or not you hold. EV0 is the name of the constructor, or the evidence constructor, or the proof that 0 is even. Right? You can notice here that we sort of said, hey, EV0 is the proof just for 0. Now EVSS says, okay, give me a natural number n, give me a hypothesis H that n is even, and then I will conclude that EVS of S of n, that is to say the successor of n is even. Right? So now we get these primitive theorems here that show us their types. Let's skip along here, and let's just see the type of EV0. It's a little small. EV0 is a proof that EV0. Let's look at the type of EVSS. That's a little big. Some Goldilocks problems over here. So EVSS says, give me a natural number n. If you can show, give me a natural number n, let me highlight it. If you can show that EVN, then EVS of S of n. If n is even, then the successor of n is even. Let's see how you might work with these. Let's start with something straightforward. Let's build the proof tree. I shouldn't say straightforward. Let's start with something on the less complex side. Let's prove that 4 is even according to our rules. Make that a little bit bigger. Great. Let's do it. Okay. We want to prove 4 is even. By EVSS, if we can show that 4 is even by showing that the predecessor of 4 is even. Right? In a sense, we're just doing backwards reasoning. If this is the type of EVSS, we have a lemma that says, hey, if you want to prove EVS of S of n, then just prove EVN. So that's why applying EVSS takes our goal from EV4 down to EV2. Now you might look and see, I can do EVSS again, and that's going to lower my 2 down to 0. Right? Because to show that 2 is even, it suffices to show that 0 is even. But we have a way to show that 0 is even. We assumed that in rule 1, EV0. Okay, so what do we know so far? These are like little mini theorems that we declared by fiat, and we can use apply with these constructors, these forms of evidence, just like we could with any other theorem that's been proved. Now, if you wanted to, you could go ahead and specify everything. So here we're going to write the entire proof object. This right here, what I have selected, is the entire proof that 4 is even. If you don't believe me, it works. Maybe this helps. Okay, why is that? Well, EV0 has the type that 0 is even. EVSS says, well, give me a number n, and then give me EV0. And then give me a proof that n is even. And then I'll tell you that the successor of n is even. So this together is a proof that 2 is even, because we give it a number 0, and a proof that 0 is even. So here we now have a proof that 2 is even. And if we do the same thing here, then we'll say, okay, we give EVSS a number 2. We give it a proof that 2 is even, and then we get out, on the whole, the proof that 4 is even. Oh, right, I have to apply it, not check it. My bad. Some sloppy tactic use. Okay, so we can do more than that. Let's next see how we can use it in a context. So you might look at these rules and say, but is this enough? You know, Prof. Greenberg, that we can get something 2 higher. What about something 4 higher? So we can prove that if n is even, then 4 higher than n is even. So here we can do a generic proof with this proposition we just defined. Okay, let's see where we are. For all n is a natural, if n is even, then we'd like to know that 4 plus n is even. Okay, let n be given. The simple here will remind us that, there's 4 successors wrapped around n. So let's remember that n is even. And now let's see, okay, EVSS, it suffices to show that merely this number is even, 2 less. EVSS, it suffices to show that n is even, but that's exactly what we've assumed. Okay, high-level picture here before I close out this video. With the inductive keyword, you can create something of type prop. You name the forms of evidence, and you get to write the rules about when your proposition is provable. Now, what we haven't yet done is related this to any sort of formal concept of evenness. Like I said, we have 2 other definitions of evenness, and we don't yet know how these relate. And, you know, the mathematician in me is just tickled to finally get to see how they relate. Once you've got two concepts for the same thing, it's one thing. 3 concepts of evenness, they really had better be the same. Right. So to return to the explanation, this inductive is a way of defining the set of rules. We saw a way to present them here in inference rules. I'm going to make a separate video about how to understand these inference rules, but really, this is what you need to interpret them as. And then you should be able to translate any inference rule to something like this. And then after that, using these custom defined inductive propositions is just like using lemmas, right? We defined a fresh proposition EV, and we said, hey, EV0, EVSS, these are our base theorems. These are the theorems for EV, and then let's just see what the consequences are together. Okay, there's a lot of videos today. There's a lot of concepts I want to explain. There's not that much actual new stuff beyond this concept of the inductive propositions. We're only going to learn 1 or 2 extra tactics, and we're not going to see that much other new things. But now that we have this tool, there's a lot to see and do because there's a lot we can state now that we weren't able to state before. So things are about to get really interesting. Next up, I've got some basic quizzes just trying to understand these proof trees, and then we'll go back to our material of learning how to work with evidence. Talk to you soon.